Now, points of inflection relates to concavity. So some graphs have points at which the concavity changes. If the tangent line to the graph exists at such a point, then that point is called a point of inflection. There are three types of points of inflection. In this case, you could have change from concave up to concave down. You can change from concave down to concave up, and you can change from concave up and concave down. Those different tangent lines, some of them might be oblique, some of them might be horizontal, some of them might be vertical. All of those tangent lines are possible, but there has to be one unique tangent line there. The concavity of f changes at the point of inflection. Note that the graph crosses the tangent line at points of inflection always. So the definition for a point of inflection, let f be a function that is continuous, and let c be a point on the interval if the graph of f has a tangent line. This, by the way, in some books they don't include that has a tangent line, and then it will change where they specify their points of inflection. But on the AP exam, and most commonly, it's defined with a tangent line at the point C, f of C. Then the point is a point of inflection of the graph f when the concavity of f changes from up to down or vice versa, down to up. So the definition of a point of inflection requires the tangent line exists at the point of inflection. So let's look at some examples. Determine if each of these labeled points constitutes a point of inflection according to the definition listed above. If no, explain why. So we have point A, B, and C. I want you to take a minute, pause the video, and check if you think there is a point of inflection. We're eyeballing, I get that. So if it's changing from concave up to concave down, or concave down to concave up, or if it's neither. Pause the video and check. All right, so I'm assuming you're back and unpaused. The answers to this is that A and B are points of inflection, but C is not. C, actually, it looks like a relative minimum in this case, or an absolute minimum in this case. The function does not change from concave up to concave down or vice versa at point C. So that's the problem there. Now, I want you to pause it and try and find the last 5 points. And I'm assuming you're back. So in point D, it changes from concave up. So we have concave up here to concave down. Then we have concave down to concave up. So you know what? At both D and E, they're both changing concavity there. However, at point D, there's definitely one tangent line there. But at point E, there's not a unique tangent line. Like you could draw one here, draw one here. So it does not have a unique tangent line. Therefore, right here, it will not have a point of inflection, even though there's a change in concavity. So in this case here, point D is a point of inflection, but point E is not, since there's not a unique tangent line at point E. For the last one here, you have concave, it's concave up and concave down, and I can draw a single tangent line, a unique tangent line there. Great, definitely that. And we have here G and H are a unique situation because it goes from concave down to linear and then linear to concave down. So there is a change in concavity. However, it has to change from concave up to concave down or vice versa. It cannot go from concave up to linear. So it's not enough to say that concavity changed because it went from concave down to something that was linear. That's true. It is a change in concavity, but it has to change from up to down or down to up to be considered a point of inflection. So that's the problem at both G and here at G and at H, that they're not changing from up to down or down to up. It's changing from down to linear and the other one from linear to down. But if corners are not points of inflection ever. All right. And the same, by the way, for cusps and things like that. They then can't be either by the same token. So how do we find these points of inflection? Well, we're looking for where then there's going to be a tangent line. Either it's going to be a tangent on the function itself that works, right? So if C of f of c is a point of inflection on the graph, it either happens where the second derivative is 0 or where it doesn't exist. A lot of times when it doesn't exist, it may not be, so we have to really check the sign of the second derivative on either side, because it could be a cusp or a point there, but we won't know. It could look like this, so it could be one of these numbers. Then it's going to give me a second derivative that's undefined, or it could be something like this here. Right now, that's going to give me undefined derivative and second derivative there, but it's not a point of inflection. So that's why it's really important that you check what's going on there. All right, so let's look at find the points of inflection. So the way to do this is basically we got to find the second derivative and look at where the second derivative is either 0 or does not exist. So job number 1 in example 3, find the first derivative, which will then help me find the second derivative. And I need to figure out where the second derivative is either 0 or undefined. In this case, it's a polynomial, so it's only going to be 0. So we're going to factor it. I did that here. Factor it and set it equal to 0. So that happens when x is equal to 0 and 2. Then I need to say, okay, I potentially have a point of inflection, but I won't know until I check. So I need to analyze it on the number line and look at the signs here. So, okay, right here, it's positive. Whoops, I didn't mean to do that. Let's try that again. I meant to just do that part. So I'm checking. So right here, I end up with a positive, then a negative, then a positive to show you those values. And I need to establish that this point here exists. That's what I wrote here, because it could potentially not exist. It could have something strange happening there. So we really have to be careful with that. All right. So then we look at what the point actually is. So I'm going to find where the point happens, substitute in f of 0. That's going to give me the point 0, 0 then is going to be a point of inflection so f of x has a point of inflection at 0, 0 since. Now, look, it is just like finding relative maxes and mins. And I'm just going to put a little side note, P.S. Points of inflection happen at relative mins and maxes of the first derivative. So if I give you the function of the first derivative and I ask you how many points of inflection are there, I want you to then, you would have to go and graph that if I gave you the actual function and count how many relative maxes and mins are there of the first derivative. So it just kind of depends what function I've given. So if I'm finding relative maxes and mins on the first derivative, I would then reason it out that I have like an increase and then the derivative is equal to 0 and then a decrease in the function. For example, for a relative maximum, well, for points of inflection, it's very similar. You do the 3 bullet points. You tell me what is happening to the second derivative on the interval right before the point of inflection, show what happens on the second derivative on the other side, and also what happens at the point. So this is kind of a little mini proof to prove that you have a point of inflection. And you have to also check at 2. So 2 does the same thing, right? So find the point. It gives me 2, -8. And then again, what's the second derivative right before the number 2? And you can't say to the left the second derivative is greater than 0, because it's not all of it to the left, that is. So you can't use the left and right descriptors. You have to be specific to the interval. You have to say on the interval from 0 to 2, the second derivative is greater than 0. You cannot just say, oh, to the left of x is equal to 2, it is going to be the concave up or down or something like that. You have to be specific. That's one thing I can tell you from the readers on the AP exam. This is what I hear a lot when I go to roundtables for this. So that's how you find points of inflection. So now let's try a similar problem. Find the points of inflection on this particular one. That means find the first and second derivatives. Pause it and try it first. It's something unique happens here, by the way. Try first and come back. And I'll show you the work for it. Here we go. So the first and second derivative, when I take the second derivative set equal to 0, it happens at 0. But when I test for the second derivatives on either side what the value is, it is positive on both sides. That means, oh wait, hang on. It's not going to change its concavity, so it's not a point of inflection. As a matter of fact, this function has no points of inflection. It actually looks like this. It flattens out here a lot, but it's not completely flat, but it does. And it's concave up everywhere, essentially, for this problem here. So using the example, use this example to answer these questions. I want you to just stop and think. If f double prime of a is equal to 0, does it mean that there's always a point of inflection at x is equal to a? Hopefully we just figured that out, that the answer to that is no. So is the converse of theorem 4.8 true, meaning that if you have the second derivative equal to 0 at a, then there must be a point of inflection? No, it's not true. Not true. So it's not, it just gives me points to check. It doesn't tell me that there are definitely ones there. So it's not enough just to say, oh, the second derivative is equal to 0, therefore it's a point of inflection. You must show what happens. That's why this part of it is explanation is super important, that we put those pieces in. You must show that the concavity changes there.